Hello everyone, this is Chao from CPAS Virginia Tech. In this video nugget, I will give a brief introduction to Simplified Optimal Trajectory Control for LLC Converter. Part 3, Optimized Burst Mode. Burst mode is widely used to improve the light load efficiency of LLC converter. The concept of a burst mode is to switch the converter between on and off mode. During burst on time, the converter runs at the efficiency optimal point, while during burst off time, the converter is shut down. The average power of a burst mode equals to the power required by the load. However, there is a problem with the conventional burst mode. We want the converter to fix to the highest efficiency load trajectory, but during burst on time, the random current is shrinking. This is because the first pulse settles random tank energy to very large. The following switching cycle corresponding to very large load condition, the trajectory will become smaller and smaller. Finally, in burst off time, it comes to burst mode initial point. This is the efficiency of a conventional burst mode. The problem is that it cannot fix to optimal point. Optimal trajectory control for burst mode is proposed by CPAS to solve this problem. It uses fixed 3-pulse pattern. The first pulse is used to settle random tank to highest efficiency load trajectory. The second pulse would follow the desired trajectory. The third pulse also follows. After that, in burst off time, it comes to burst mode initial point. So SOTC for burst mode uses fixed 3-pulse pattern. But there would be a problem with the digital implementation of SOTC. During on time, only the last 2 pulses deliver power. For a given controller, there would be a minimum off-time limitation of 5 microseconds plus 1/4 of a random period. This limitation would cause a maximum burst duty cycle corresponding to a maximum burst average power. This curve is the maximum burst duty cycle versus random frequency. For 130 kHz LLC converter, the maximum burst duty cycle is more than 50%, which is not a problem. For 500 kHz LLC converter, the maximum burst duty cycle is around 26%, which means if burst power is 60%, maximum burst average power is only 16%. To solve this problem, adaptive multi-step according to load condition is used to increase the maximum burst duty cycle. The basic control scheme are still the same. This is an efficiency curve. State-of-art burst mode has some improvement over normal operation, and the proposed optimized burst mode can further increase the efficiency. With the 3-pulse pattern, burst mode range is quite limited. We can use 5-pulse or 7-pulse to increase burst operation range until burst mode efficiency curve touches normal operation efficiency curve. The converter enters burst mode at 26% load and can achieve 91.8% efficiency at even 2.4% load. This is a 500 kHz LLC converter. The input is 400 watt. The output is 12 volt. Battery transformer is used for high output current design. The 60 MHz microcontroller is mounted on the power stage. A current sensing resistor is used to sense low current to determine burst mode pulse number. This is a burst mode waveform with a 3-pulse pattern under 4 ampere load. From top to bottom, the waveforms are primary high-side driving signal, random current, low current, and output voltage. This is a 5-pulse burst mode pattern under 12 ampere load. And this is a 7-pulse burst mode pattern under 17 ampere load. For all conditions, random current is settled to around the optimal point. That's all for my video nugget. Thank you.